So our next talk is the last of the day, and it's a brief community sharing presentation. And I think it's a combo deal, so we get both Stu Bishop and Andrea Fassbender. I guess you both need to be mic'd up, and we need to get that up on the screen. They're going to be talking to us about a carbon hotspot.
Can you actually? Yeah, I'll hold it. Slide advancer. And if you want to both have pointers, I don't know who wants to advance slides.
Sure. All right, so it's a pleasure to be here to talk about our interests in Western boundary currents and carbon sequestration. And so I think Marina gave a nice talk on some of the things that we think are important in these systems for carbon uptake. And this is a collaborative effort with lots of folks from PMEL in Japan and Scripps in China as well. And I'm Stu Bishop from NC State. I'm a physical oceanographer.
And I'm Andrea Fassbender. I'm currently a postdoc at NOAA PMEL. I'll be starting at Mbari in fall. And so today we want to tell you about these ideas, and we're currently calling it Carbon Hotspot. It's a field program to understand biophysical drivers of carbon sequestration in Western boundary current regions. And so just to give you a little bit of the motivation for why we're interested in this, here we've plotted the mean annual sea air CO2 flux, which we saw earlier as well. And on the right, we have the surface eddy kinetic energy. And what you'll notice, these different symbols here, or these letters, are different Western boundary current regions. And in all of these regions, notice the map is blue, and that's where CO2 is going into the ocean annually. In addition, if you look at the eddy flux map, you can see that these areas are also places where we have high kinetic energy from eddies, so lots of eddy activity. In addition, all these areas are within the subtropics, but near the subpolar boundary, and they're areas of mode water formation. And so we have regions that are large carbon sinks, areas where mode waters are formed, so waters at the surface are immediately subducted, and areas where eddies are interacting in these fields. And so one of our goals is, through this project, is to develop an interdisciplinary and international research community to facilitate better understanding of the role that Western boundary currents play in climate and carbon sequestration. And the primary question we're kind of aiming to get at is how do biophysical interactions, eddies, and mode water formation influence ocean carbon sequestration as they interact in these regions?
So I'll provide a little bit of motivation. So we have measurements at Kershaw Extension Observatory, and that's located just south of Kershaw Extension Jet. And so one of the things we know about the Kershaw Extension is that it goes through these transitions between strongly and weakly meandering states. And Bo Chu from Hawaii was the first to show one of these sort of spaghetti diagrams. And this is an update in Oka et al. 2015. These are bi-weekly snapshots of the Kershaw Extension Jet. You can see from 1993 and 94, in the first 1,000 kilometers east of Japan, that the jet more or less took the same pathway, and it was in what we call this stable state. And then in 95 to 2001, it took a more erratic state and was meandering quite vigorously, and then it transitioned again a few more times. And so what we're finding out, too, is that this also has strong impacts on subtropical mode water variability and formation. So mode water are these thick water masses that form on the equatorward side of all western boundary currents. So these thick water masses of nearly uniform temperature, they form during the winter months from intense heat loss, and they subduct down along ice-thickened surfaces and reside just above thermocline. And then during the summer months, you have surface heating, and it caps off this communication. So these water masses don't interact with the surface until the following winter. And one of the processes, this process is what we think is one of the most important processes for sequestering CO2 in these regions. And so as an example, I plot here, these are marks. This is kind of the time of year when we expect your maximum mud water formation. This is sea surface height and color contours. The black solid line is what we're calling the axis of the Kershaw extension. And then the magenta lines, if they're shown up well, I've plotted the 16 to 18 degrees C SST surfaces. So in the North Pacific, 17 degrees is roughly the temperature of the mud water, and analogous to 18-degree water in the Gulf Stream. So in 2007, from 2008 to 2010, you have a much restricted area that's outcropping. And that had a dramatic effect on how much mode water was formed during these particular years. Then in 2011 to present, we had more of a stable state in the Kershaw extension. You can see that the mouth of the range just opened wide up, so the ocean is sucking in a lot more CO2, we think, during these time periods. Let's see. Another piece of the puzzle that's come out more recently is looking at the implications for chlorophyll A. So this is kind of also showing that we don't have very good coverage because of clouds. This is two different time periods. In 2008, when you had a vigorously meandering state, and then in 2011, when you had more of the stable period. So plotted as MODIS, chlorophyll A, and this is just the March average composite. And then 2011 as well. So one of the things found, though, since, on an annual average state in Lynn 2014, they found this connection between chlorophyll A and stable states. So they found that there was about a 12% higher chlorophyll A relative to multi-year mean when you're in these unstable states. So when there's more eddies around, we're getting more chlorophyll A at the surface. And they linked this to the propagation of wind-induced Rossby waves from the Central Pacific. But these are going to be your large-scale sort of driving mechanism. What we think, too, is at play is really these submesoscale features that are associated with these more enhanced eddies in the region. And it's these submesoscales that are really prevalent, and they are on the time scales that can lead to vertical adduction of things into the aesthetic zone. Also, another piece of evidence from OCA 2015 is that they've linked the decadal variability in mode water to also biogeochemistry. There's a line south of Japan, I don't know if this has a marker, but there's a line south of Japan where they do routine shipboard measurements, and they found that there have been correlations with more biogeochemistry variability associated with this mode water. So if you take a cross-section of these two time periods, and you look at the temperature structure, so I took the Argo 1 degree by 1 degree, so it's a pretty coarse product, but it's the best sort of representation of the subsurface we have at these times. Look at the March average, and you have a dramatic decrease in surface area, the outcrops. And these are the 25 to 25.5 isopicomal surfaces in black, and then the temperature contours down to 1,000 meters. And compared to 2008, 2011 has a lot more open area to expose to the atmosphere. So one of the mechanisms I think, or we think is going on is that it's really, these mixed layers have a lot more eddies, and when you have a lot more eddies, you're going to have a lot more filaments and fronts associated with these eddies, which can lead to potentially mixed layer instabilities associated with the submesoscale. So this is a schematic looking at the mixed layer in the top 100 meters or so, and then you have the isopicomal surfaces that outcrop, and then they expose the subtropical mode water layer. Once mode water is formed, it's free to evolve into the ocean interior, and we think that mesoscale eddy stirring would be a large portion of that process. But at the surface in particular, these mixed layer instabilities will act to re-stratify the mixed layer, and so it would effectively cap off communication during these time periods. I must note, though, that in a review paper, there also can be downfront wind and surface cooling that can counter this, so it's not clear whether these processes, which one wins out in this case.
All right, so another thing to think about in terms of the biogeochemistry that's going on in mode water formation regions is how this influences carbon uptake. And so this is showing data from the Kershaw Extension Observatory, and it's showing the delta PCO2 over time. The blue is the in situ data, red is a running mean, and the gray bar areas are highlighting the peak of the spring productive period, which is about from March to April. The lower plot is showing density surfaces here also over time, and the colors are showing the volume of subtropical mode water. So as Stu mentioned, in 2008 and 2009, the Kuroshio was in an unstable state, and so there was less mode water formation. And since 2010, it's been in a more stable state, and there's a large expansion of the formation. And up here, what you'll notice in particular at first is that there's a large negative delta PCO2, suggesting this area is a large sink for atmospheric CO2. You can also see some blips here due to biological productivity that bring that delta PCO2 even lower. These cross marks here are showing time periods when the mode water is outcropping at the Kuroshio Observatory, so at the Keio mooring, whereas I have to note that this is from Argo floats in a slightly different region, so they don't perfectly align. But the important thing to note is that the outcrop time is really when you have the biological productivity period. And so what's interesting is we'd like to know how are the biology influencing the waters before they're subducted and put into the interior of the ocean. And that can be through particle export going on. That can also just be through depression of the delta PCO2 causing larger air sea flux. And so we're interested in learning more about those dynamics. And so at this point, we've submitted a score proposal for a working group, and that is under open review. You can access it at this website and provide feedback. In addition, we have been talking to folks at CLIVAR, and the Process Study and Model Improvement Panel has endorsed us and encouraged us to submit a proposal for a CLIVAR work group. So that's something we'll be doing in September. So if you have any interest in this, please come talk to us about it and give us feedback. In addition to this, so the goal of this will ultimately, if we get enough community support beyond the group we've already coordinated, would be to have a process study in the Kuroshio region. So this is our fancy schematic for that. And so to get to this point, there's a lot of things that happen before that, including getting community feedback. But we have also been encouraged by our Japanese collaborators to submit a proposal to get ship time with them in 2018 to do a pilot study where we could go out and figure out how difficult it's going to be to resolve these mesoscale features and sub-mesoscale features in both space and time.
Yeah, so one of the things we're thinking is do a glider path that has this bow tie fashion. So in the Papa buoy, Charlie Erickson and Mel Pelland did this for over a 2-year process study, and they found that the gradients associated with the mesoscale by having the gliders were up to 10 times higher than climatology and can even change sign. So having these point measurements might not be enough, and it would be really interesting to go out with a suite of instruments such as sea gliders that can get the sort of mesoscale structure. And then PMEL has a sail drone that can measure surface fluxes of CO2 and also heat fluxes, and they can cruise at about 100 kilometers per day. So you can have these things just whipping around and can get the large scale or the sub-mesoscale structure associated with the mesoscale that we hope to resolve with the gliders.
So please come talk to us. We have a poster, or just find us anytime during the conference.
We'll take any questions. Thank you. We can talk everyone.